Dear students, let us discuss about the effect of conjugation on absorption wavelength of conjugated hydrocarbons, even the compounds which are having conjugation. Uh, see, generally the electron promotion takes place from HOMO to LUMO in organic molecules. In a molecule, generally HOMO is highly occupied molecular orbital. LUMO is lowly unoccupied molecular orbital. HOMO, in general to speak, is a ground state where from the electron will participate in excitation to LUMO. LUMO is a activated state. So, if the HOMO and LUMO gap matches with the energy of radiation, that is simply to say the delta E of uh, electronic levels, if it is matches with the electromagnetic radiation, then energy transformation takes place from the electromagnetic radiation to the molecule. So here, to happen electron promotion, if the energy gap is matched with the energy of electromagnetic radiation pertaining to ultraviolet and visible region, so molecule absorb the energy and the electrons undergoes to the activation. So this is the criteria the molecule has to exhibit. So let us see the electron transition regarding to sigma bonding molecular orbital to sigma star anti-bonding molecular orbital in hydrogen molecule. Hydrogen is a molecule, or simply we can say it as an element. So this homo-LUMO in hydrogen molecule, homo-LUMO gap is energy gap is equals to 258 kilocalories per mole, which is corresponds to the energy of radiation having the wavelength value is equals to 111 nanometer. Generally, we can calculate the energy of radiation by the formula E is equals to h nu. E is equals to h nu. E is energy of the photon or energy of the radiation. H is Planck's constant. It is equals to 6.624 into 10 to the power of minus 34 joules. Even we can say it as 6.624 into 10 to the power of 27 minus 27 eggs, 10 to the power of minus 34 joules, 10 to the power of minus 27 eggs. H is a Planck's constant, that value already we have discussed, and nu is the frequency. Nu can be converted into wavelength value, that is equals to nu is equals to c by lambda here. Let me write here. See, E is equals to h nu. So here this is energy, this E is equals to energy, this is Planck's constant, this is frequency. So this frequency can be written as nu is equals to c by lambda. Lambda, c is velocity of light, that is 10 to the power of 8 meters per second. So if you want to convert it into a kilometer, then we will get 10 to the power of 5 kilometers per second. So the speed of light, lambda is equals to wavelength of radiation. So if you substitute this new value into this equation, then we will get E is equals to h c by lambda. So with this equation, we can able to calculate the energy of that radiation when it is provided in wavelength value. Anyway, h is Planck's constant, c is velocity of light. These are two constant values. So by substituting Planck's constant and velocity of light, we can able to calculate the energy of radiation. So 111 nanometers wavelength containing radiation contains the energy that is equals to 258 kilocalories per mole. So that here you can see, we can calculate the energy in, we can able to calculate the energy in calories also, joules, eggs, even you can convert the value into calories also, right? So hydrogen is a molecule contain a single covalent bond between two hydrogens. So this is the hydrogen, the energy difference. This is the HOMO, you can see sigma bonding molecular orbital, highly occupied molecular orbital. We have two hydrogens in the bond. So here one electron, by absorbing the energy, by absorbing the radiation, uh, its wavelength is 111 nanometer, and its energy is equals to 258 kilocalories per mole. So the electron is promoting into sigma star antibonding molecular orbital, sigma star antibonding molecular orbital. So this is sigma to sigma star transition. So these are the basic things the molecule has to undergo from HOMO to LUMO promotion. So here what we have learned about to observe the electromagnetic radiation, the energy gap between HOMO and LUMO must be tallied. It must be equals to the energy of the radiation. Then only the energy transformation from electromagnetic radiation to the molecule takes place. So this is the information regarding to sigma star electron transition. Even in other organic molecules also, if we find only or exclusively sigma bonds in them, so that molecules exclusively undergoes to the sigma bonding electronic transition from sigma bonding molecular orbital to sigma star antibonding molecular orbital. Okay, so here the energy difference is more for sigma and sigma star antibonding molecular orbital. No other electron transition requires this much quantity of energy for its electron promotion or for its electron transition. So electron transitions are very much important physical processes happening in the molecule. Therefore, they will provide the bands. They will form the bands in a monitor of ultraviolet visible spectroscopy, so that according to that bands we will analyze, we will construct the structure of a molecule. We will construct in the sense, UV visible spectroscopy is a tool with which we will identify the presence of chromophoric unit. Even some oxochromes also there, then we could able to we could also able to identify the presence of oxochromes on the chromophoric molecule. Then let us discuss about the 5 to 5 star transition. When a double bonded molecule such as ethene absorbs light, it undergoes to the 5 to 5 star electron transition. So 5 to 5 star electron transition is taking place here in alkene molecules. There are, if the conjugated double bonds are there, then conjugation will influence the absorption wavelength of the radiation, that we will discuss in coming slide. So whenever only the 5 bonding electrons are there, only in the sense the 5 bond will exist on sigma bond. Once the sigma bond is formed in the molecule, and there would be a possibility for the existence of 5 bond in the molecule, so that the molecule will undergoes to the 5 to 5 star electron transition first. Then if there is a possibility to participate the molecule even in sigma to sigma star electron transition also, that is possible. But the initially the generating electron transition is that 5 to 5 star electron transition. So because the 5 to 5 star energy gap is narrower than sigma to sigma star gap, ethene absorbs the light at 165 nanometer, a longer wavelength than a molecular hydrogen. 165 nanometer wavelength containing radiation will provide the energy for the ethene molecule to participate that molecule in 5 to 5 star electron transition. Now you can see the energy gap between HOMO and LUMO is 173 kilocalories per mole. 173 kilocalories per mole. So in a previous case, that is in the case of hydrogen molecule, the energy gap between HOMO, highly occupied molecular orbital, and a lowly unoccupied molecular orbital is 258 kilocalories per mole. Whereas in the case of HOMO-LUMO gap of ethene molecule, the energy difference is 173 kilocalories per mole only. So that quantity of energy can be provided by the ultraviolet light, which is having 165 nanometers. 165 nanometers. Even you see the case of hydrogen molecule, the molecule does not absorb the radiation in ultraviolet visible region. Even this ethene molecule will also not absorb the radiation in the range of UV visible. 165 nanometer is not in the range of UV visible radiation. It is below to the UV visible radiation. Far UV region it is. So mid UV region or near UV region. Uh, near UV region. There are three classifications in the ultraviolet region. That after we will get the radiation pertaining to visible region, that is 380 nanometers to 750 nanometers. So on this slide we will get the information regarding to the energy of radiation, which is quantitatively related with the energy gap of HOMO and LUMO. Energy gap between HOMO and LUMO. Once the energy gap between HOMO and LUMO is more, then more energy containing radiation is needed for the electron promotion. Therefore, less wavelength containing or smaller wavelength containing radiation will be absorbed by the molecule. If the energy gap is narrow or energy gap is small between HOMO and LUMO, so less amount of energy is needed and more wavelength containing radiation will be absorbed by the molecule for its electron transition. Right. Let us discuss about the absorption frequency of 1, 3 butadiene. Absorption wavelength. Even frequency, if you say the value in frequency terms also, we can identify the energy, because frequency, wavelength, and energy, these three properties, even wave number also, these properties are interrelated with one another. Interrelated with one another. So here 1, 3 butadiene, the energy, there are two bonding molecular orbital levels and two anti-bonding molecular orbital level. So psi1, psi2, these are the two wave functions related to bonding molecular orbital. Psi3 and psi4, which are the levels related to anti-bonding molecular orbital. Here psi3 is the LUMO, lowly unoccupied molecular orbital, but not psi4. So energy gap between psi2 and psi3, HOMO and LUMO, is 132 kilocalories only, whereas in the case of ethene it is equals to 173 kilocalories per mole. In the case of butadiene, 1, 3 butadiene, the energy gap between HOMO and LUMO is 132 kilocalories per mole. Energy gap is reduced. Energy gap is reduced. It is because of delocalization of conjugated double bonds in the molecule. So this is the main important thing that we have to remember whenever the molecule undergoes to the delocalization or molecule undergoes to a conjugation. So there will be a decreased energy gap between HOMO and LUMO. Once the energy gap is decreased, so that the radiation observed by the molecule for the electron promotion from HOMO to LUMO will also be less. Energy required is less, so that the molecule absorbs at longer wavelength. The molecule absorbs the radiation at longer wavelength. So by absorbing the 132 kilocalories per mole energy containing radiation, that is equals to the radiation having 217 nanometer wavelength. So electron promotion taking place from HOMO to LUMO, so that it is 5 to 5 star electron transition. 5 to 5 star electron transition. Of course, sigma to sigma star electron transition needs more energy. 5 to 5 star electron transition requires moderate or less energy. Even N to 5 star transition again requires very less energy. So for the promotion of sigma to sigma, for the electron transition of sigma to sigma star, sigma to sigma star, very less wavelength containing radiation is required. For the promotion of electron from 5 bonding molecular orbital to 5 star anti-bonding molecular orbital, the energy required is moderate or less, we can say. And similarly, the electron promotion from non-bonding molecular orbital to 5 star anti-bonding molecular orbital, the energy required is very less, so that molecule absorb the radiation at longer wavelengths. Let us go for one more molecule. 1 comma 3 comma 5 hexatriene. One more double bond is increased in the molecule. So here the 5 to 5 star electron transition is taking place because we have two kinds of electrons, two types of electrons, sigma bonding electrons and 5 bonding electrons. Anyway, sigma bonding electrons, they tightly held together, held with the molecule. 5 bonding electrons, they are loosely held with the molecule, because bond energy of a sigma bond is more compared to the bond energy of a 5 bond. Carbon carbon sigma bond is more energetic than carbon carbon sigma bond. Generally a sigma, sorry, carbon carbon 5 bond, generally a carbon carbon single 5 bond does not exist because 5 bond is not a independent bond. Once a carbon and carbon sigma bond formed, depending upon that, during the lateral overlapping, during the partial overlapping of pz orbitals or px orbitals, the between pz or px orbitals of the two carbon atoms, the two adjacent carbon atoms which are already bonded with a single covalent bond, there will be a formation of one more 5 bond. There will be a formation of one more. So 5 bond is not a dependent bond. Sorry, 5 bond is a dependent bond. Dependent bond, listen carefully, it's an important one. 5 bond is a dependent bond. It will depends upon the sigma bond. Unless sigma bond is not there between two carbon atoms, 5 bond will not form. But sigma bond is a independent bond. It is not a dependent bond, independent bond. There is no requirement of any other bonds for its formation. Once the energy of the two atoms orbitals or hybridized orbitals of the two atoms of the molecules matched, then the two hybridized orbitals or atomic orbitals, they undergoes to the overlapping, that two terminal overlapping. So there will be a result of a single covalent bond formation between the two carbon atoms, right? Here there are 3 5 bonds, that too they are in the conjugation. Generally dienes are classified into 3 types: isolated dienes, cumulated dienes, and conjugated dienes. Isolated, let me write the structure of these 3 category. See here, for example, if a molecule is like this, see here we have a double bond. Even again we have a double bond at third carbon in the sense from the second double bonded carbon atom, or of course if you give the numbering from here, 1 2 3 fourth carbon. If the diene system present at 1,4 position, it is a double bonded molecule or double bonds containing molecule. Two double bonds are there, but they have separated with a CH2 moiety. Here we have two hydrogen atoms at middle carbon atom. So this diene system or this molecule is example for isolated diene. What diene it is? Isolated diene. Got it? So these two phi systems are isolated by one CH2 moiety. This is isolated diene, right? It is one example. Cumulated diene. Cumulated diene means the two double bonds, they present on same carbon atom. This is one double bond. Even if you have this double bond also, like carbon, CH2, this is CH2, and this is also CH2, right? So these are the two phi bonds or two double bonds. It is also example for a diene, but two double bonds present on the same carbon atom, Therefore this diene system is example, this molecule is example for cumulated diene. Cumulated diene. So first one is isolated diene, second one is cumulated diene, and third one and most important one is conjugated diene. See, this is a double bond and this is also a double bond. There are four carbon atoms in the molecule. One, two, three, four. Four carbons are there. These two double bonds are separated with a single covalent bond. So one after one, carbon after carbon, the double bonds are present. This system, this kind of arrangement of there, this kind of double bonds arrangement is there in the molecule. That molecule is a example for conjugated diene. What diene that is? Conjugated diene. So conjugated diene molecule, it will be influenced by means uh, to identify the nature of this conjugated diene, how many double bonds are there in a molecule, whether are there in conjugation or not, we can identify this arrangement in a molecule through UV visible spectroscopy. So this delocalization. Okay, here it is example for conjugated diene. Let us discuss about what is the reason for the decreasing of absorption energy when a molecule is conjugated one. We will discuss later. Right. So here it is a conjugated diene. Even here it is also a conjugated diene. You can see this is the double bond and this is also a double bond. These two double bonds are separated with a single covalent bond. So these two double bonds are there in conjugation. Even this double bond is there again conjugation with a third double bond, because these two double bonds also they are separated with a single covalent bond. Therefore it is also example for a conjugated double bond. Means three double bonds are there at 1 comma 3 comma 5 position and they are in conjugation. So what happens because of this conjugative arrangement of double bonds, they will participate in delocalization in the sense the double bond or pi bonding electrons present between first and second carbon, they moves in between second and third carbon. Similarly, the bond or 5 bonded electrons or 5 bond present between third and fourth carbon again moves onto the fourth and fifth carbon atom, and due to this shift of double bond, the 5 bond present at fifth position moves onto the carbon atom. Therefore, we will get a molecule like, so here we will get a double bond, here also we will get a double bond. This carbon will attain a negative charge, unit negative charge. This carbon anyway lose the 5 bonding electron, so it will get a positive charge. So that after immediately the negative charged electrons undergoes to the delocalization with 5 bonding electrons, so that again we will get the initial molecule. So this kind of delocalization continuously takes place between uncharged conjugated molecule to charged conjugated molecule. So this delocalization of conjugated double bond, they will reduce the energy between homo and lumo, homo and lumo. So this is the main factor due to which the absorption wavelength value for the conjugated dienes will be at longer wavelength. For suppose, yeah, we have discussed about the previous molecule ethene. The energy required is 173 kilocalories per mole. Here for 1 comma 3 butadiene molecule, there is no conjugation for this molecule, ethene molecule, but for 1 comma 3 butadiene molecule, one conjugation is there, one extra double bond is there, that double bond is there in conjugation, so that delocalization of electrons takes place, during which the homo-lumo gap will decrease, so that the energy difference between homo and lumo, this is the homo and this is the lumo, so that the energy gap is equals to 132 kilocalories per mole. Again, one more conjugated double bond is introduced. One more conjugated double bond is introduced. The molecule is 1 comma 3 comma 5 hexatriene. 1 comma 3 comma 5 hexatriene, so that its energy or the energy difference between homo and lumo is equals to just 111 kilocalories per mole or 111 kilocalories per mole. So even if we increase, if the molecule contain one more double bond, that is 1 comma 3 comma 5 comma 7 uh, mm, uh, octatetraene, if a molecule is 1 comma 3 comma 5 comma 7 octatetraene, then the required energy for homo or promotion of electron from homo to lumo again decreased. Energy required for the transition again decreased, and the molecule absorbed the UV visible radiation at longer wavelengths. So here the previous compound ethene molecule observed the light at 111 nanometer wavelength, and 1 comma 3 butadiene is absorbing the radiation at 217 nanometer wavelength, and even 1 comma 3 comma 5 hexatriene molecule is absorbing the wavelength or the light which is having the wavelength equals to 258 nanometers. So in this way the conjugation decrease the energy gap between homo and lumo, therefore the amount of energy needed for that transition is also reduced. Let us have a example of uh, uh, aldehyde ketone molecule. The ketone molecule is 4 methyl 3 pentene 2 one. 4 methyl 1 2 3 4 5. 1 2 3 4 5, or even you can give the numbering from here also. 1 2 3 4 5. Giving numbering from this methyl group is convenient one, because According to IUPAC nomenclature, the carbonyl group is will be given least number. Carbonyl carbon will be given least number. Based on that, we can give the number either from left to right or from right to left. But the carbonyl carbon has to get least number. In the case of aldehydes, that is a different scenario because aldehyde anyway present at the terminus of molecule, so that the numbering will be started from aldehydic carbon only. But in the case of ketone in the sense the carbonyl carbon anyway present in the middle of chain, so that carbonyl carbon has to get least number. In such a way the numbering will be given, so that here uh, we have a methyl substituent at fourth carbon, so it is a 4 methyl. A double bond is there at third carbon, 3 in 2 pentanone or pentane 2-one, its IUPAC name. So molecule participate in N to 5 star transition as well as 5 to 5 star transition also. But the 5 to 5 star transition is influenced by the conjugation because this 5 bonding electrons are there in conjugation with this 5 bonding electrons. Let me show the 5 bond. These 5 bonding electrons, they are there in conjugation with the 5 bond electrons or 5 bonded electrons present between carbon and oxygen. Therefore, they will undergoes to the delocalization. They will undergoes to the delocalization. This is the phenomena will takes place at room temperature, at room temperature only, at 25 degrees Celsius temperature. No need to, there is no need of providing energy to the molecule. At room temperature, the delocalization of this conjugated 5 bonded electrons takes place million times. So that is the main deciding factor, or that is the main reason for the decrease of homo-lumo gap in the molecule. This is the way the conjugated system or conjugated double bond will influence the molecule to absorb the radiation at longer wavelength. See, right here you can see uh, uh, 5 to 5 star transition, it will takes place. See, UV gives rise to a strong UV absorbance at 236 nanometer due to a 5 to 5 star transition. So we will see a N to 5 star transition at 314 nanometer. N to 5 star transition means it is non-bonding molecular orbital level. It is 5 bonding molecular orbital level. So the energy gap, you can clearly see this is the energy gap for 5 to 5 star electron transition, whereas this is only the energy gap for N to 5 star electron transition. So when the electron present in Psi2 level undergoes to the promotion to Psi3 level, that transition is called as pi to pi star transition of this 4 methyl 3 in pentane to one. But here, of course, because of this conjugated double bond, the energy required for this 5 to 5 star electron transition is 91, uh, the energy gap is somewhat which is equals to the radiation, that is equals to 236 nanometer wavelength. So even into 5 star transition will also be influenced. Anyway, you see the energy gap between 5 bonding molecular orbital to 5 star anti-bonding molecular orbital decreasing means even the energy gap between non-bonding molecular orbital to 5 star anti-bonding molecular orbital will also decrease. Because of that reason, the N to 5 star electron transition taking place at 91 kilocalories per mole and energy containing radiation. for which it will absorb the radiation having 314 nanometers wavelength. So this is the way the conjugation influences the absorption wavelength of a molecule. So far we have studied about how a conjugated double bond or how a extended conjugation increasing the absorption wavelength of a molecule. Simple thing that we have to remember is once the conjugation increased, one conjugated double bond is there. So the energy gap between HOMO and LUMO decreases. So that 5 to 5 star transition requires less energy, therefore molecule absorbs at longer wavelength. Even if molecule contains one more double bond, conjugated double bonds like 1 comma 3 comma 5 hexatriene, then again there is a decrease in energy between HOMO and LUMO. For that, the 5 to for the 5 to 5 star transition to happen, it requires again less energy. And if you go on increasing the conjugation in a molecule, so HOMO LUMO gap decreases and 5 to 5 star electron transition takes place readily. So far, this is the information I would like to discuss about you all people. So I am concluding this presentation by this at this point. In from next session onwards, let us discuss about infrared spectroscopy. Thank you very much.